Okay, we're going to look now at finding roots of equations. So roots are just a fancy way of saying where does it cross the x-axis. So if you remember back to AS, you used the discriminant to find if there was two equal roots, if there was no real roots, or if there was a repeated root. So this is just a method of finding the roots of an equation. So if you think about, let's just think about a very dodgy graph. Okay, if we have a graph here, f of x, finding roots means we want to find out when f of x equals naught. Okay, so if we look at points along that curve, so if we look at a point here and a point here, you're going to see that the y value will be different. Okay, our x's are both negative, but our y value, because it crosses the x-axis, our y value will go from a negative here to a positive here. Same thing over here. If we look at just before and just after the root where it crosses the x-axis, the y value is positive on this first one, and then it'll be negative here. Okay, so the y value will change sign, and that's a way of telling if there is a root in that position. Okay, so our first example, show that 2 plus x squared minus x cubed equals naught has a root between 1 and 2, and then by considering change of sign, find the root to one decimal place. Now this is going to be really similar to trial and improvement that you did in the junior school. So our function is that equation 2 plus x squared minus x cubed. So we want to find that there's a root between 1 and 2. So if we find f of 1, so 2 plus 1 squared minus 1 cubed, we'll get 2. Now, we're not worried so much about the number, we're worried about the sign. So f of 2 then is going to be 2 plus 2 squared minus 2 cubed, and we get minus 2. And we say that there's a change of sign, therefore there's a root between 1 and 2. So that's the first part of that question sorted out. Now by considering change of sign, find the root to one decimal place. So we'll just continue on to get, and this is where it's like trial and improvement. So we go to between 1 and 2, 1.5. So when we put 1.5 in as x, we get 0.875. Put f of 1.6, we get 0.464. F of 1.7 minus 0.023. Okay, so we know that the root is somewhere, the sign is changed, so the root is somewhere between 1.6 and 1.7 if we drew out the graph. Just pick which one's closer to 0. So our answer, you can see 1.7 gets us closer to 0 than 1.6 does. So the root is 1.7 to one decimal place. Our second one then, show that sine theta plus cos theta equals 1 has a root between 1 and 2. So the first thing we're going to need to do is to bring this 1 over so it equals naught. So we'd say f of x equals sine theta plus cos theta minus 1. Now whenever we have trig involved in this, it's always radians. Okay, always radians. So we want to find f of 1, sine 1 plus cos 1 minus 1, and it gives us 0.3818. F of 2 then. But it just so happens that both examples that I've picked are between 1 and 2. It doesn't have to be between those two numbers. Sine 2 plus cos 2 minus 1. And when we put that in, we get minus 0.5068. We say that there's a change in sign. And you need to put this wee line in. therefore a root between 1 and 2. And then to go on to find it to one decimal place, try f of 1.5. So put that in, we get 0.0682. So f of 1.6 then is minus 0.0206. So we know there's a change of sign, so it's going to be in between those two. And 1.6 gets us closer to 0. So 1.6 is our root to one decimal place. Okay, and this is one of the questions that it can ask you to write sentences and stuff like that. But one of the conditions for this would be the graph has to be continuous. Okay, so it's a normal graph is continuous. Think if you're x cubed or anything like that there. One that would have a discontinuity would be something like your reciprocal graph, where there's a break in it, okay? Problems can come up, okay, so these are the issues that if the curve touches the x-axis, so it has a repeated root, there's a problem because obviously if something had a repeated root, the y value just before and just after are both going to be negative. Okay, so that would cause a problem. If several roots are close together, that could cause a problem. So in the two examples that we've done, we've looked at the root between 1 and 2, but what happens if there's more than one root there? That can cause a problem. Okay, so sometimes a question will ask, well, what's the condition the graph is continuous, and what problems could arise if using this when you're using this method? The curve could touch the x-axis, or you could have several roots close together. So that would usually be the first part of the question over with, and then it leads you on to this next part of the question, which is Newton-Raphson approximations. So it states that if XR is a good approximation for a root of f of x equals 0, then x of r plus 1, which equals xr minus f xr over differential of f xr gives a better approximation. Okay, so this would be like part 2 of the question. Okay, so our example then, to use this Newton-Raphson method to determine the root of the equation x cubed minus x equals 2 in the range minus 2 to 2, given your answer correct to 3 decimal places. Okay, so our f of x, remember, has to equal 0, so x cubed minus x minus 2, bringing that across. So we want to find this in the range. We want to find where the change of sign is first. So quite often in an exam, it's separated into the two different part 1 and part 2 of the question. In this example, it's all one. So f of minus 2, so putting that into our f of x, we get minus 8. F of minus 1, we get minus 2. F of 0, we get minus 2. F of 1, we get minus 2. And f of 2, when we put 2 in, we get 4. So our change of sign, so remember this is usually the first part of a exam question, the change of sign, so that means that there's a root between 1 and 2. Okay, so we're going to take that it's 1 as our starting point. So that's our approximation of the root. It's at 1, and then we're going to use Newton-Raphson to give us a better approximation. Okay, so to apply the Newton-Raphson, you need to have f of x, which is x cubed minus x minus 2, and we also need to have the differential of that. So we get 3x squared minus 1. Okay, so our Newton-Raphson, which remember you get in your formula booklet. You don't have to learn this, you just have to learn how to apply it. Now sometimes in an exam it'll say apply Newton-Raphson 2 times or 3 times to get an approximation for a root. But in this case it says find your answer to 3 decimal places. So we keep going until the 3 decimal places are the same. Okay, so our first approximation, we said it was between 1 and 2, so our first approximation is 1. So that means our next approximation is going to be 1 minus, and now we put 1 into x cubed minus x minus 2, so 1 cubed minus 1 minus 2 over 3 times 1 squared minus 1, and it turns out to be 2. X of x2, then we're going to put our previous answer in, so we get 2 minus 2 cubed minus 2 minus 2 all over 3 times 2 squared minus 1, and we get 1.63636. Then when we go into x3, we use 1.63636. Now keep it as like the answer on your calculator screen and makes it easier. So it's 1.63 etc. minus, and then put that into f and put it into the differential, and we get that it's 1.53039. Then repeat it. So x4, we're using now 1.53 etc. And when we put that in, we get 1.52144. Go again, and we get 1.52138. Now hopefully you can see these two here. We have the same answer to 3 decimal places. So we say our answer is 1.521. So if it just tells you to do it to a certain number of decimal places, you keep repeating it until you get that it's the same 3 decimal places. But in an exam, it could just say repeat it 3 times or repeat it 4 times, and you just write down that answer.